Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi and today we are going to talk on module that is types of refractories under the paper glass and glass ceramics. So students, let us see what we are going to learn in this module. So we will be learning about silica bricks, alumina silica refractories, fire clay refractories, high alumina refractories. Then we will be learning about magnesite refractories, chromite refractories, chrome magnesite refractories, and further we will be learning about magnesite chrome refractories, silicon carbide refractories, and carbon refractories. So in the following, we describe some important refractory materials and we will be discussing with the silica bricks. So before moving to silica bricks, we will discuss some of the basic part. On the volume basis, the production of the silica bricks is next only to the fire bricks, which we will be discussing in the later slides. They can be considered as a part of Al2O3SiO2 refractories but are described here separately for clarity. Silica bricks. On the volume basis, the production of the silica bricks is next only to the fire bricks, which we will discuss later on in this module. They can be considered as a part of the Al2O3SiO2 refractories but are described here separately for clarity. The raw material for the silica bricks is the mineral quartzite or ganister. It is mixed with about 2% lime, that is CaO, and the firing is done at 1500 degrees Celsius. Lime reacts with some silica to give liquid calcium silicate, that is CaSiO3, which on cooling forms a glass and bonds the grains. After cooling, the brick consists of 5 to 10% glass and the rest is cristobalite and tridymite. The silica brick has exceptionally high thermal shock resistance above 800 degrees Celsius. Below this temperature, due to a high thermal coefficient of expansion, it has a poor thermal shock resistance and the heating and cooling between room temperature and 800 degrees Celsius must be done very slowly. Silica bricks, therefore, are not used in applications where frequent shutdowns or cooling below 800 degrees Celsius is required. The alumina silica phase diagram, which we have already discussed, shows that a low melting point eutectic forms near the silica end of the phase diagram. That is, small amount of alumina will lead to the formation of eutectic and degrade the brick. For this reason, super silica bricks which have low alumina content through raw material selection are used in high temperature applications. Such bricks retain nearly their full strength almost up to their fusion point, which is 1685 to 1800 degrees Celsius. The application of the silica bricks is in open hearth furnaces for steel making, roofs for glass furnaces, coke ovens, reverberatory furnaces for copper melting, and so on. Alumina silica refractories. Now we will discuss about alumina silica refractories. So there are various type of alumina refractories. Refractories in alumina silica, that is Al2O3 SiO2 system, vary in composition from nearly pure silica, as in brick silica, which is greater than 93% silica, to nearly pure alumina, as in corundum refractories, which is greater than 99% alumina. Most of the refractories in this category are prepared from fire clay, a class of minerals containing mostly alumina and silica. So students, you can see the table which gives the summary of alumina silica refractories. So there are different types of refractories which includes fire clay, high alumina, mullite refractories, corundum refractories and silica brick. Their compositions are also mentioned on the right hand side. Fire clay refractories. Fire clay refractories are produced in maximum quantity amongst all refractories. They are made from fire clay, which is essentially hydrated aluminium silicate. An important fire clay is kaolinite with formula Al2O3SiO2.2H2O. On heating, the water is driven off between 450 degrees Celsius to 550 degrees Celsius, leaving a calcined product with 45.9% alumina and 54.1% silica. Invariably, there are small amount of impurities in any clay in the form of compounds of iron, calcium, magnesium, titanium, sodium and potassium. The clays used for refractories can be graded as hard or flint clays and plastic clays and also in between. The hard clays undergo less shrinkage on heating. The composition of the clays from different sources can vary widely. It can vary SiO2 from 45 to 90%, Al2O3 from 5 to 35%, and together with varying amount of other impurities. The starting materials for fire clay refractories consist of a mixture of hard and plastic clays as well as calcined clays. The presence of calcined clays reduces the drying and firing shrinkage. The fraction of the different constituents is chosen to yield the desired composition and the type of fire brick being manufactured, like super duty, high duty, medium duty or low duty, which we have discussed previously in the table. The raw materials are crushed and ground, tempered with water and formed in the desired shape, followed by firing in the temperature range varying from 1100 degrees Celsius to 1400 degrees Celsius. About 75% of the refractories manufactured below to the fire clay refractories, they are used in the iron and steel industry, non-ferrous metallurgy, glass industry, pottery and cement industries. An important consideration in their application is that they start losing their strength at about 300 degrees Celsius below their PCE temperature, unlike other refractories which retain their strength at temperatures much closer to the PCE. High alumina refractories. As mentioned before, the fire clay refractories begin to lose their strength at temperatures about 300 degrees Celsius, which is below their PCE. For refractories that are able to withstand higher temperatures and also have higher slag resistance and abrasion resistance, alumina silica refractories with greater than 47.5% alumina are used. These are called high alumina refractories. The raw materials for the high alumina refractories are clays such as kyanite, andalusite, sillimanite, diaspore, clay, bauxite and crystalline alumina or corundum. The first three have different crystal structure, but all have the chemical formula Al2O3SiO2. Diaspore clays consist of diaspore, that is alpha AlOOH mineral bonded by fire clay substance with an alumina content higher than 63%. Bauxite is an aluminium ore. It consists mostly of the minerals bauxite AlOH whole thrice, boehmite gamma AlOOH and diaspore alpha AlOOH mixed with some clay, that is collinite, and some amount of oxides of iron and titanium. It is the main source for the metal aluminium. The refractory grade bauxite after calcination contains 87% Al2O3, 5.5% SiO2 and 3% each FeO and TiO2. Some clays such as kyanite must be used after calcination to reduce the shrinkage. To prepare the refractory materials, a mixture of the available raw materials is selected to yield the desired composition and properties. The crushed and graded material is mixed with some amount of plastic clay, pasted into desired shapes and fired. The shapes or the phases present after firing are mostly mullite and glass with some amount of corundum, cristobalite and possibly some tridymite depending on the time and temperature of firing. The properties such as slag resistance, strength, constancy of volume depend on the phases and their amounts. Two types of high alumina refractories are given special names because they contain especially a single phase. These are mullite refractories and corundum refractories. Pure mullite has the chemical composition given by 3Al2O3.2SiO2, which corresponds to 71.8% alumina and 28.2% silica. The extent to which the mullite phase develops on firing depends on the purity of the raw material and the firing conditions. Mullite refractories have excellent volume stability and strength at high temperatures. They are used in electrical furnace, roofs, blast furnace, hot metal cars and superstructures of glass tank furnace. The refractories containing 99% alumina consist of single-phase polycrystalline alumina are called corundum refractories. Magnesite refractories. The raw material for the magnesite refractories are magnesite rock and the magnesia formed and obtained from seawater. Pure magnesite rock has the composition of 17.6% magnesia and 52.4% CO2. It is calcined at high temperatures to drive off CO2. This product called dead burnt magnesia, which can be used as such in the form of granules to make monolithic refractories or can be used for making bricks and other shapes. For making bricks or other shapes, the dead burnt magnesia is ground and graded into different particle sizes. These grades are then mixed in a desired ratio. The two types of products can be made. In the first type, the bonding is produced due to sintering during firing, while in the other, the bonding is a chemical bonding. In the first case, the ground mass is tempered with water to make it moldable. It is then molded into desired shape in a power process. After this, drying and firing is carried out. In the second type, a very small percent of chrome is added to the ground powder. It is then molded into shapes and dried. No firing is done. The bricks undergo firing during the actual use and approach the properties of the fired product. The magnesia refractories have a fusion point of 2150 degrees Celsius, which is the highest amongst the common refractories. And because of these basic nature, they are useful for application below the slag line. Chromite refractories. As we know, chrome ore consists of highly refractory spinel with the general formula MON2O3, where M is a divalent metal like magnesium Mg, iron Fe, and so on, and N is a trivalent metal like chromium, aluminium, and so on. The compound chromite, that is FeOCr2O3, is the major constituent. The ore also contains hydrated magnesium silicate, usually the mineral called serpentine, having the composition 3MgO.2SiO2.2H2O. The usual range of composition of chromite ore is given in this table. So students, you can see that the percentage vary with the component. For example, for Cr2O3, the percentage component is 30 to 50%, whereas for SiO2 it is 4 to 8. So on firing, the glass 3MgO.2SiO2 forms, which provides the bonding between the grains. This glass is silica rich and has a low melting point. The chromite bricks have therefore a low refractoriness. They have good resistance to basic slags and to iron oxides below about 1540 degrees Celsius, that is 1540 degrees Celsius. They are less expensive than magnesite refractories and are used in metallurgical furnaces where the conditions are less severe. Now students, let's discuss about chrome magnesite refractories. Addition of magnesite to the chrome ore results in the formation of MgO SiO2 glass, which is richer in MgO. And as can be predicted from MgO SiO2 phase diagram, it has a higher melting point. Addition of about 30% of magnesite to the chrome ore results in a refractory material which can withstand load at temperatures higher than 1700 degrees Celsius. This material can withstand corrosive slags and can be used in the critical paths for high temperature furnaces. Now comes magnesite chrome refractories. These contain the composition of magnesia greater than 60% and it has 8 to 18% of Cr2O3. They also have high temperature resistance, good spalling resistance, and can be used with basic slags in steel making. Silicon carbide refractories. Silicon carbide is produced by reacting sand and coke in an electric resistance furnace. Silicon carbide exists in several polymorphs. The two major polymorphs are alpha silicon carbide, that is alpha SiC, which has a hexagonal structure like woodsite, and beta SiC, which has a zinc blende structure like diamond. Of the two, the alpha phase is marginally more stable than beta polymorph. In refractories, the silicon carbide exists in its alpha form. The silicon carbide has several useful properties. Its thermal coefficient of expansion is very low and its thermal conductivity is very high, about 10 times that of fire bricks, which makes it highly resistant to thermal shock. It retains high strength at high temperatures and has high fracture roughness. It is inert to attack from most chemicals and slags. Its only drawback is it oxidizes slowly in an oxidizing atmosphere. It is still possible to use it in air up to quite high temperatures, that is up to 17-20 degrees Celsius under certain conditions, and almost up to its dissociation temperatures, that is 2400 to 2700 degrees Celsius in the inert atmospheres. So this is in continuation with silicon carbide refractories, which we are discussing in the previous slide. The chemical bond in silicon carbide is covalent in nature. It therefore does not sinter. Various types of bonds are employed to prepare silicon carbide refractory shapes, and these are: first is self-bonded silicon carbide. The article made of silicon carbide grains and carbon powder is heated in silicon vapor. The silicon carbide, which forms deposits around the silicon carbide grains and forms a bond. Next is clay bonded. Clay is used as a bond. The refractories of this product is limited due to the low melting point of the glass that is present. Next is silicon nitride bonded silicon carbide. The silicon nitride, which forms deposits around the silicon carbide grains and forms a bond. The major chemical species and the phases present in these materials: of the material listed in the table, those bonded with clay and listed in the last row are the easiest to produce and are used in maximum tonnage quantity. Despite their tendency to oxidize, the silicon carbide refractory can be used in air to quite high temperatures due to what is called the passive oxidation. At a pressure of oxygen less than 1 bar, the oxidation reaction proceeds. The SiO2 is lost by vaporization and there is loss of mass. This oxidation is called active oxidation. However, at slightly higher pressures of oxygen, that is greater than 1 bar, which is more usual, the reaction, that is 2SiC plus 3O2 gives 2SiO2 plus 2CO, occurs. The SiO2 formed in this case forms a layer on the refractory piece and prevents its further oxidation to temperatures which approach the melting point of SiO2. Because of their properties which we have discussed, silicon carbide refractories are used in diverse applications such as metallurgical heating and melting furnaces, kiln furnitures including tiles and other shapes used to support the ceramic ware during firing in the kiln, retorts, muffles, recuperators tubes, shields and thermocouple tubes are some other applications where reducing atmosphere exists. Carbon refractories. Carbon as a refractory material has some following unique combination of properties. First, carbon does not melt, it sublimes at 3500 degrees Celsius. It is not wetted by most metals and slags. It has a low coefficient of thermal expansion, which gives a high thermal shock resistance. It has a high thermal conductivity and excellent resistance to attack by most acids and bases. However, it can be used only in highly reducing atmospheres because it oxidizes in air at temperatures greater than 450 degrees Celsius. The raw materials for carbon refractories are high quality coke, anthracite coal, and natural and artificial graphite. Binders used in the manufacturing process are pitch, tar, or resin. In some grades, additives like silicon carbide, silicon, or Al2O3 are also used. The carbon refractories are used in aluminium industry to line the aluminium electrolytic tank in the ferroalloy and the silicon industry. Moreover, it is also used in blast furnace hearths and various other applications. So students, let's now summarize what we have learned in this module. So in this module, some important classes of refractories have been discussed, and the first class was silica brick. Silica bricks are manufactured in large quantities and they are only next to the fire bricks. The best part of the silica brick is that they can go to the high thermal shock resistance, which is above 8000 degrees Celsius. In the super silica bricks, the amount of alumina is kept very low to avoid low melting eutectics. Some bricks can be used for their fusion points, which is around 1685 to 18,000 degrees Celsius, and a large class of refractories belong to alumina silica system. These range from pure silica, which we have discussed before, to almost pure alumina called corundum. In this system, the refractories manufactured in the largest amount are the fire clay refractories or fire bricks. The overall composition of the fire clay refractories is silica, which is less than 678%, and alumina, which is less than 44%, and the remaining is other compounds. The fire clay refractories containing higher amount of alumina have higher PCE temperature. The raw materials for the fire clay refractories are fire clays, and an important example is kaolinite. The composition of the clays from different sources can vary widely, from SiO2 that varies from 45 to 90%, and for AlO2O3 from 5 to 35%, together with varying amount of other impurities in the form of compounds of iron, calcium, magnesium, and so on. However, these type of refractories start losing their strength at 3000 degrees Celsius, which is below PCE, unlike other refractories which maintain their strength almost up to their PCE. So the alumina silica refractories containing greater than 47.5% alumina are called high alumina refractories. Further, we have discussed about mullite refractories, which are used for higher temperatures than fire clays. Further, we have discussed the corundum refractories. The pure mullite has a composition with 71.8% alumina and 28.2% silica. The refractories containing 99% alumina consist of single-phase polycrystalline alumina, which are called corundum refractories. Further, we have discussed the magnesite refractories, which are made from magnesite ore. Moving further, we have discussed magnesite refractories are basic in nature and are used in the basic hearth furnaces below the slag line and in various other applications. Then we have discussed the chromite refractories, which are made from chrome ore. The bonding is provided by magnesium silicate glass and they are less refractories than the magnesia bricks. Therefore, they can be used in applications where basic refractories with lower use temperatures are needed. So, the silica carbide refractories comes into picture, which are made by heating sand and coke in an electric furnace. These refractories have a very high thermal shock resistance over other refractories, and therefore the next refractories called carbon refractories are there, which have excellent thermal shock resistance as compared to silicon carbide. Thank you.